Hello. Today we shall be speaking about limits, and this lecture, in fact, is an important one. It's crucial because this is the real beginning of calculus. Before that, in the ancient eras, all the phenomena were continuous, smooth, and the functions, the relations are perfect. But then, in order to establish or to derive the two concept of differentiation and integration, then you have to resort to the concept of limit, as we said before. Now, we shall start first by the sequence, because there is great analogy between sequence and functions. And when you say the limit of a function, you may also say it in a different way. You can say, for example, the long behavior, for example, of a function, if it exists, of course. Or you can say, for example, the convergence of sequence as well. Now, in this lecture, we shall be speaking about the limit of a sequence first, then the limit of a function, and then the meaning of one-sided limit, if it exists, and the infinite valued limits and limits at infinity. Now, what's the limit, the meaning of the limit of a sequence? Now, the limit of a sequence, it means that your sequence approaches a certain value as it's a prolonged behavior. As the sequence go on and on, you tend to a certain value. First of all, you have to define a sequence. A sequence, as it's said here, it's a function defined on the set of natural numbers. In other words, for each value of n, each element of n, you have a value in R. So to every element in a real function, this constitutes a one-to-one correspondence between n and a real function, capital S of n, which is the element of the sequence. So it's a function of domain n and range a subset of R. So we shall give examples. For example, if you express, for example, S is equal to, in which Sn, the element is equal to n, it means that you have 1, 2, 3, etc., since you have here n element in n. For instance, for example, this is another sequence. Sn is equal to 1 over n. Now, 1 over n means that you start taking n1, then 2, then 3. When n is 1, you get 1. When n is 2, you get half. When n is 3, you get 1/3, etc. You notice here that this sequence approaches the value 0. It's never equal to 0, but it goes down to 0. So we say that this sequence converges to 0, or it accumulates to the value 0. For example, this is another sequence. Sometimes the sequence is given in terms of brackets, and they ask you to get the closed form of the sequence, or they give you instead the closed form, and you have to expand it to find all the elements of the sequence. For example, this sequence, is called a geometric series, and this geometric series, it's convergent. Why it's convergent, we shall see this. But this is the ratio here. Each element is equal to half the one preceding it. So we can express this as 1 over 2 to the power n. So when s is equal to 1, you get half. 2, you get 1 over 4, 3, you get 1 over 8, etc. And this sequence, if it is an infinite sequence, then it converges again as a series is something, but as a sequence, it converges again to 0. Now, this is the sequence again. You start with 1 half, 1/4, 1 over 8, etc. You find out that it approaches the value 0. It's never equal to 0, but you always approach the value 0. So we say that 0 is the limit of this sequence. This is another sequence here. This sequence, the first term is 2 minus 1, the second 2 plus half, the third 2 minus third. You can express it in this form, and you can try. You can check. When n is equal to 1, you get 1. When n is equal to 2, you get this is positive over 2, so you get this term here, etc. And this sequence, if you notice it, as n gets very large, this becomes smaller. So it tends to 2, but it oscillates around 2. Sometimes it's greater than 2, sometimes it's less than 2, depending on n. When n is even, it's greater. When n is odd, it's less than 2. So it looks something like this. It starts with 1, 2.5, it goes on, and then it converges to the value 2. How did we know that it converged? And what's the meaning of convergence? And again, this value of 2, what does it mean? Well, the value of 2 is the value at which to which the sequence converges. It approaches the value 2. So this value of 2, to be the limit of this sequence, it has to satisfy a certain criterion. The criterion is that the more we approach 2, the more you find infinite number of elements of the sequence. For example, you can take a neighborhood of the value 2, here, which is value 2 and something, 2 plus epsilon and 2 minus epsilon. And this 2 plus epsilon and 2 minus epsilon, if you take epsilon large, then you may take as many elements of the sequence. But the more epsilon becomes smaller, the more you exclude elements. But this doesn't apply to the value 2. The value 2, even if epsilon is very small, you still can find an infinite number of elements of the sequence, provided that you take more terms, and this is always satisfied, especially for the point at which the sequence tends to. Now, a sequence, now this is the definition of a sequence. A sequence is set convergent if by increasing n, the term Sn, etc., Sn plus 1, Sn plus 2, all the elements after an n and so on tend to a definite number L. That is, for any interval L minus epsilon, L plus epsilon, we saw this before, you take 2 minus epsilon, 2 plus epsilon. Now, which we choose around L. Whatever, even if epsilon is small, you may exclude some elements of S, but again, you always find an infinite number of its elements inside. If we can do so, then this is the term, this is the limit of the sequence. Actually, this doesn't apply to other elements of the sequence. It's only the value 0. Although 0 may not be an element of the sequence, but still, in other words, it's a deleted neighborhood, like we said in the our second lecture. You exclude the value 2, but you still around 2, you find also always an infinite number of elements of this sequence. For example, here you have this is a method called the fixed point theorem, and the fixed point theorem is one of the known numerical methods to calculate roots of functions. For example, here you have, for example, g of x is equal to cosine x and y is equal to x, and you want to obtain the root of x is equal to cosine x. In other words, you solve these two equations together to get the root. What you do is that you choose any point here, for example, this one, and then you apply the fixed point. How? You start to obtain a better approximation. This is the root, by the way. So you want to approach the root. So you reach P1, and then you do again another approximation. You get P2, etc., and you get P3, P4, etc., until you nest the root into an interval. The more you go into, the more you choose more points, or the more your sequence accelerates or proceeds, the more you nest your root into smaller and smaller intervals. And this point, which is where the root exists, is the only point on X is at which, when you choose any interval around it, deleted interval, for example, you will find an infinite number of elements of this sequence, which is P0, P1, P2, etc. So you say that this is the limit of this sequence, and actually the limit is the root of the two equations when they are solved together. And so we say that here there is a convergence, and we call this principle in mathematics the contraction principle. Now, so as we said, if we choose around L any neighborhood, not necessarily including L, you always find an infinite number of elements of the sequence. Here it is. Here is again L. This is the sequence again. Here you have Sn. Here this is S1, this is S2, S3, etc. And this is the presupposed limit, because you don't know whether the sequence has a limit or not. But then, if it has a limit, then if you choose any epsilon around L, you always find elements of the sequence. Suppose then you decrease epsilon. You decrease epsilon so that you exclude S2, and here S1 is already excluded, and you decrease it more and more to exclude this term S3, and you exclude this term. Still, if you even exclude these 5 or 6 or 7 terms, you will find by increasing n that there are more terms that are included in this deleted neighborhood of L, and therefore you say that the value L is the limit of this sequence. And that's the meaning really of the limit of a sequence. Now, to give you a more example, now suppose, for example, you have a sequence 10 to the minus n. In other words, you have 10 to the minus 1, minus 2, minus 3, and we say that it converges towards 0. How did you know that it converges towards 0? Now, this is, for example, 10 to the minus 8, and still we are proceeding towards the value 0. You get here 10 to the minus 9, then 10 to the minus 10. Suppose, I am supposing that 10 to the minus 9 is the limit of this sequence. Is this true? How do we know that this is the limit of the sequence? All you have to do, as I said, you take any neighborhood around the point 10 to the minus 9, and you check whether there are an infinite number of elements of the sequence. Here, no, there are no one single element when you exclude the term 10 to the minus 9, because this interval here excludes this point and excludes this point as well. So you don't have any sequence. Whereas if you approach 0, 0 is the only point at which when you take any neighborhood, here it is, here is the point 0, and you're approaching the point 0. Now, this is the point 0, so what you can do is that you can take any neighborhood, like for example, epsilon, and you can always find 10 to the minus n less than epsilon. How? If you choose n greater than the logarithm of 1 over epsilon, then you are sure that this term 10 to the minus n will be somewhere here. So for all values of n greater than log 1 over epsilon, you are sure to find as many terms as you wish here. Of course, you may take, for example, epsilon 10 to the minus 17. So it means that n greater or equal to 18, all of these terms are etc., which means the elements 10 to the minus 18, 19, 20, etc., will always be in the neighborhood of the point 0. So you say that the point 0 is the limit of this sequence. Thus, if a relation exists between n and epsilon, such that when n decreases, one can increase n, so that we can always find element as n inside the neighborhood, L minus epsilon, L plus epsilon, it proved that the sequence converges and that the limit is equal to L. For example, prove that 1 over n is 0. How can you prove this when n tends to infinity is equal to 0? Now, the presupposed limit is 0. So what we do, we check the difference between 1 over n and 0. Can we make this as small as possible, less than epsilon? If we take an integer n that depends on epsilon, yes, indeed. Since here, to satisfy this, in order this to hold, you have to have n greater than 1 over epsilon. So if there exists a natural number n greater than 1 over epsilon, and for all n, for all element of the sequence, starting from number n and ors, which are greater than capital N, which is the natural number n, then you are sure that this always holds, or that the difference between 1 over n and 0 always is less than the prescribed value epsilon. And this is the way how you check the convergence or the limit of certain sequence. Now, what about the limit of function? Exactly the same. There is a kind of analogy here. The functions, for example, this is the function that is not defined at the point A. Doesn't matter. That the function is defined at the point is not the important thing. The important thing, whereas when x approaches A in a deleted neighborhood of the point A, does f of x approach the point R or the value L? If this is so, then we say that the function has a limit at the point x equal to A. For example, this is sine x over x, and you want to find the limit when x tends to 0. When it tends to 0 from both sides. We say that it approaches 1. How we do know that? All you have to do, we take values that are near 0, plus or minus 0.1, plus or minus 0.01, etc., and you keep decreasing x towards 0. You find that f of x approaches almost the value 1. Of course, we cannot rely on such a concept or a numerical calculations to calculate the limit. We have to prove it more rigorously. But anyway, this gives you an impression how a function like this has a limit. This function has a limit approach to the value 1, although it's already is not defined at the point x equal to 0. So the important thing is not the definition of the function at the point 0. It's like 10 to the minus n. It may not have a value equal to 0, but it approaches 0 as we proceed further and further by increasing the number n. We can all find in a deleted neighborhood of the point 0 as many elements as we wish of the sequence. So a real number L is said to be a limit of f, or that the limit of f of x when x tends to A is equal to L, if for all epsilon greater than 0, there exists a delta of epsilon such that when x lies in the open interval from A minus delta to A plus delta, and x not equal to A, in other words, the deleted neighborhood, because you're not interested whether f is defined at A or not, you want to approach A from the right and from the left, and you see whether f of x approaches a value L, or it lies always in the neighborhood L minus epsilon, L and n plus epsilon. If this is so, then the function has a limit. Here, for example, here the function, you take a point x here, in the open interval from A minus delta and A plus delta. Here, for example, we took a function which is not defined at A, and there is a hole here. It's not defined at A, but if x approaches the point A from the right or from the left, you find that f of x itself approaches the value L from the right and left. So you say that the function has a limit. Now, to show you this with an animated applet, the one that we had at Cairo University. Now, this is a function here, x cubed minus x squared at x minus 1. This is a function that is not defined at x equal 1. But this is not the important thing. The important thing is that whether it has a limit. In other words, when x tends to 1, and it's not equal to 1. And this is why I'm teaching my students, I'm telling them, when you take the limit, you have in mind that the function may not be defined on 1. You say it approaches the value of 1, but it's not equal to 1. So here it's not equal to 1, but this function, since it's not equal to 1, x is never equal to 1, you can cancel from numerator and denominator x equal to 1, and you end up in the numerator with x squared. So this function is the same function as x squared, provided that x is not equal to 1. So can I make sure, how do I know that this function has a limit at x, at the point x equal to 1? All I have to do is you approach the point equal to 1 from the right and left. Here, you approach 1. If you approach the point 1 from the right and left, you find that f of x itself approached the value L from the right, from upper and lower. If it approaches the value L, then you say that your function has a limit. If it doesn't, then your function has no limit at x tends to the point A. Now, suppose, for example, you have another function like 1 over x. Now, 1 over x, here it has an asymptote, vertical asymptote at the point equal 0. Does this function has a limit at the point x equals 0? Now, we do the same thing. We approach the point 0 from in a deleted neighborhood, of course, doesn't matter. But we approach the point 0 from the right and from the left. Here we find that epsilon, as delta becomes smaller, epsilon goes to infinity. So we conclude that this function has no limit. You have to have when epsilon tends to 0, or the opposite, when delta tends to 0. Epsilon or tends to 0, they are approached together so that we can bound. So if you can bound x in the neighborhood of A, you bound f of x in the neighborhood of L, then you can conclude then that the function has a limit. And so the previous has a limit at x equal to 1, and this one has no limit at x tends to 0. Now, suppose we take an example. Now, 2x minus 7, when x tends to 6, does this has a limit? Of course, this function is defined at the point x equal to 6, but it's not of importance. The important thing, it may not be defined. The important thing, does it approach the value 7 at x approach 6? So what we do, we subtract from 2x minus 5 the value 7, and we try to see whether this is less than epsilon when x minus 6 is less than delta. Of course, because 2x minus 5 minus 12 is equivalent to this. But this tells you what? Tells you if x minus 6 less than epsilon over 2. In other words, you have a point x in a deleted neighborhood of the point 6 and of radius epsilon over 2. So you take delta less than epsilon over 2. So if delta is less than epsilon over 2, what will happen? X, which exists in the deleted neighborhood of the point 6, makes this holds, or this also holds. In other words, makes 2x minus 5 in a deleted neighborhood of the point 7. And therefore, since this is true, then it means that your function here has a limit at the point x equal to 6. So in this example, although the function is defined at x equal to 6, this is of no importance. The idea is to approach x, to let x approach 6, and to let the function itself approach the so-called limit which you seek to find whether it exists or not. Here, for example, you have another function, limit of x squared minus 16 divided by x minus 4, when x tends to 4. Now, here, this function is not defined at the point x equal to 4. Yes, but doesn't matter. This is not the issue. The issue is that this approach a certain limit, and this limit equals to 8. Now, the idea of the epsilon delta mechanism which we use to prove the value of the existence of the limit. But if you only are interested in finding the limit, then this is another story, and it's much simpler. But here we try to prove that the limit exists and is equal to 8. So what we do, we take a deleted neighborhood of the point x equal to 4. So you have 4 minus delta from the right and 4 plus delta here. Down here you have a deleted neighborhood of the point 4, and you try to approach the point 4 from the right and left, and you see if the value of the function approaches the point 8. also from upper and lower in a deleted neighborhood of the point 8. Now here x squared minus 16 over x minus 4. Now since we say a deleted neighborhood, and this again I'm saying that you are not interested in the value of x in the value of the function at 4 because it does not exist. But this value, which is x squared minus 16, you can decompose the numerator is equal to x minus 4 times x plus 4, and you can cancel out x minus 4 from both the numerator and denominator. Why? Why you can cancel here x minus 4? Because you're interested in a deleted neighborhood of the point 4. In other words, you are not interested of the value of the function at 4. So this value, which is x squared minus 16 divided by x squared minus 4, is exactly equal to x plus 4. They are the same here, but provided that x is not equal to 4, and that's the case because you are approaching the point 4 in a deleted neighborhood. In other words, you are approaching the point 4 without being equal to 4. So what you can say, you can say this. You can say that x squared minus 16 divided by x minus 4 minus the value 8. Here it's the same as x plus 4 minus 8, which is x minus 4. So if this is equal to less than delta, then this is always also the same, also less than delta, because here this is what? This is equal, this, so long that x is not equal to 4, so the numerator would be equal to x minus 4 times x plus 4, and this cancels out, and you end up with the same x plus 4 minus h, which is x minus 4. And this is exactly your deleted neighborhood around the point x minus 4. So the idea is that x squared minus 16 divided by x minus 4, it will approach the point, the value 8 in a deleted neighborhood of the point 4, because the same function, this function, and x plus 4 are the same so long that x is not equal to 4. So we can say now directly that limit when x tends to 4, i.e. x is not equal to 4, of x squared minus 16 divided by x minus 4 is equal to 8. Prove that limit of modulus x over x does not exist. We want to prove whether the limit exists or no. Suppose that the limit exists is equal to L. So what we do is that we want the difference between modulus x over x, which is the value of the function, minus L less than epsilon, provided that x lies in a deleted neighborhood of the point x equal to 0. Now this presupposes that this exists, that this inequality exists. So can this really exist? Of course it doesn't. Why? Because by choosing the sign of L, suppose we don't know the value of L, but suppose L is positive or negative. Suppose it is negative, and you choose x to be positive from the right-hand side. So this is positive, and it is less than value which is negative, so it can't happen. And if you choose L to be positive, you can choose x from the left-hand side. And of course, you cannot have something negative greater than something positive. So we said that since you can make the sign of x different from L, this disqualifies the inequality, and therefore this limit of this function at the point 0 does not exist. And you see here that it approaches 1 from the right-hand side, and it approaches minus 1 from the left-hand side. So the limit does not exist. So in order that a function has a limit at a point, is that if you take any deleted neighborhood, and whether you approach from the right-hand side or from the left-hand side, you should approach one definite, and that's important, one definite value L, and this value is finite, not infinity. This value is finite, and therefore you can say that the limit exists. So this function here has no limit at the point x equal to 0. So the limit exists from both sides, and the value of f of x in this example tends from the right to 1 and from the left to minus 1. Since both limits are unequal, the limit does not exist at x equal to 0. So we come now to an important definition of limit. A necessary and sufficient condition that f has a limit at a point A is that the limit from the right-hand side is equal to the limit from the left-hand side. So if this happens, then you say that the function has one definite limit and that the limit of the function exists. Calculate the limit of f from the right and left sides at x equal 2 and 0, at the point x equal 2 and the point equal to 0. Now we shall not, of course we can use the definition of limits here, epsilon delta mechanism, but why should we? Here we have three rules. When x less than 0, you have minus modulus x plus 1, which is this rule here, the graph here, then you have x squared, a parabola here, then you have another one here, which is straight line. So when x approaches 0 from the left-hand side, here it's equal to 1 directly, because you put x equal to 0 here. But from the right-hand side, you put 0 here, so you get 0. Now from at 2, at the point 2, from the left-hand side, you use this one, you get 4. Whereas from the right-hand side, you use this one. You get what? You get 3 over 2. So this function has no limit, neither at the point 0 nor at the point 2, because here the limits are unequal, and here too the limits are unequal. Sometimes the function exists only from one side. Like for example, you have something like this, square root of 1 minus x. This function the domain of this function is x less than or equal to 1. And if you want to investigate the limit of this function at point 1, for example, you have to take a deleted neighborhood, but intersecting with the domain of the function. So here you take 1 minus delta and 1 plus delta, and you exclude 1. So in fact, what you do, you end up with the open neighborhood 1 minus delta till 1, an open interval from 1 minus delta and 1, and you investigate the function here. And you take the limit from what? From the left-hand side, because the right-hand side limit does not exist. The function here is not defined here on the right-hand side of 1. So the limit of this function must be equal to what? Must be equal to 0. So we say here that the function has a limit at x equal to 1. Sometimes the limit does not exist, but the function goes to infinity, increase without bound. So although precisely we have to state that limits, in order to exist, must tend to a definite value, sometimes we do it for convenience. We say that the limit goes to infinity. In other words, that the function increase without bound. So we call this infinite valued limits. Like for example, that this one here. Here, for example, the limit, here we say that the limits are evaluated at a point from the left and right, as I said, must be equal to a definite value L. But sometimes it happens that f increases without bound, or we wish to evaluate it when x tends to infinity. So we call the limit either infinite value limits or the limits or the second limits at infinity. And in other words, we have two kinds of limits. Either the limit when x tends to a point, we find that the function increase without or decrease without bound, or the other one, when x itself tends to infinity, the function tends to a definite value L. Like this one here, for example, 1 over x. It tends to the right to infinity and to the left to minus infinity. Whereas 1 over x squared, it tends to the right and left to infinity. It doesn't mean here that because those two are unequal, that here we don't have a limit, whereas here we have a limit. No, it's not true. Neither of both the function has a limit. Because you can't say that infinity equals to infinity, because infinity minus infinity is not equal to 0. It's one of the undetermined quantity, as we shall see later on. So neither of this nor that, this function has a limit, but yet we can say that the limit of 1 over x squared as x tends to 0 from the right or left tends to infinity, whereas here tends to infinity from the right and minus infinity from the left. Like this. Here, the function here tends to infinity from the right, whereas here it tends to infinity from the left. Here it tends to minus infinity from the right, and the other one tends to infinity from the left. For example, the tan x. We saw this before, the function tan x. It has, these are called asymptotes. The value at which the function tends to infinity, we call them asymptotes. So here the function here, it approaches it goes to minus infinity from the right-hand side of pi by 2, and from the left-hand side of pi by 2, it leads to infinity. And same thing here, at minus pi by 2 from the right, minus infinity, and from the left, it goes to infinity. Sometimes this is a different kind of, this is called an horizontal asymptote. So we saw before a vertical asymptote in the sense that when x approaches a point, we find that the function increases without bound. Here it's different. Here the function approaches a certain bound, yet when x itself approaches, goes to infinity. Because what? Because you can always find, suppose for example you have 1 over x squared, for example, 1 over x squared tending to 0. So 1 over x squared, when 1 over x squared tending to 0, you can say this, 1 over x squared minus 0. Can I make this less than a quantity epsilon? Yes, by taking x greater than 1 over square root of epsilon. So if I define a certain number m greater than 1 over epsilon, then all values of x greater than this will make the value of 1 over x squared approached the value epsilon within a predetermined quantity epsilon. And actually this value of epsilon, you can take it as small as you wish. The more you take it smaller, the more you have to increase x so that you always can bound the value of the function in the neighborhood of the point 0. If you can do that, then, and the more you approach 0, the more you lessen epsilon, and the more you take x, you find that 1 over x squared always is in the neighborhood of the point 0, then you are sure that there is a limit. So this here, this function here, you find that it oscillates like this, and then it approaches the value L. So we say that L is an horizontal asymptote of the function. For example, this function here, sine of x over x, has an horizontal asymptote. Why? Because sine x over x, we know that you can prove this here. You have sine x is always less than equal to 1, greater than minus 1. If you divide by x, then you have this less than 1 over x squared, or I'm sorry, modulus x minus 1 over modulus x. So it means that this is 1 over modulus x and 1 over minus modulus x. You can have, this is sine x2. It means that it oscillates and it has horizontal asymptote. This is an horizontal asymptote as x tends to infinity. So you can say that limit as x tends to infinity of sine x over x is equal to 0. This, we call this an horizontal asymptote of the function because the function approaches the value 0 as x tends to infinity. Here we have two kinds of asymptote. You have a horizontal asymptote. And how do we do this, as a matter of fact? How we obtain an horizontal asymptote? Well, the simplest thing is that, for example, for this function, x squared minus 1 with x tends to infinity, you put it in you divide by x squared, so you have like this 1 over 1 minus x squared. So now, when x tends to infinity, you can distribute the limit in the numerator and denominator because both they exist. This tends to 0 and this tends to 0, so you get 1. So it means that the function has an horizontal asymptote, and that's the horizontal asymptote. The one here, the dash here, the horizontal line here is an horizontal asymptote. But it also has a vertical asymptote. How would I know that? Because you have the denominator is equal to 0 at the point 1, at the point minus 1. An horizontal asymptote you obtain by taking the limit when x tends to infinity. Whereas a vertical asymptote, it's easy. What you do is that you can check the roots of the denominator, provided that the numerator at these roots are not equal to 0. So if the numerator is not equal to 0 at the roots of the denominator, then you have what you call a vertical asymptote. So this function here had two vertical asymptotes at 1 and minus 1, whereas it has one horizontal asymptote. This function here, it has what we call an oblique asymptote. So in fact, what you have all kinds of asymptotes. As we said before, you have this function here. Let us take this function, for example. You have x cubed minus 2x squared plus x plus 1 divided by x squared plus 1. Of course, had this in the denominator being equal to x squared minus 1, then you would have, in fact, two asymptotes at 1 and 1 minus 1, but you have here x squared plus 1. So there is no roots in the denominator. Then there are no vertical asymptotes. Again, there are no horizontal asymptotes. Why? Because when you take the limit at x tends to infinity, you got infinity. How would I know that? Because the degree of the numerator is greater than the degree of the denominator. So when you take the limit at x tends to infinity, you find infinity. But then when the degree of the numerator is higher by 1 of that of the numerator, when the degree of the numerator is higher by 1, the degree of the denominator, here you have 3 and here you have 2, then you are sure that there is a horizontal asymptote. And you can divide the numerator by the denominator to obtain x minus 3. You do a long division divided by plus 3 over x squared plus 1. What we did here, as a matter of fact, is that we make a long division of the numerator divided by the denominator. So you get at the end x minus 2 plus 3 over x squared plus 1. Now suppose you take the limit when x tends to infinity. What do you obtain? Of course, this tends to 0, because here you have x squared. So there remain x minus 2. Yes, it goes, of course, the function goes to infinity, but it approaches the line y is equal to x minus 2. And that's the idea. The idea is that you approach this line here. So we say, since this line is an oblique line, so we say that the function has an oblique asymptote. So functions may have a vertical asymptote, like the one we saw before. It may have an horizontal asymptote. It may have an oblique asymptote. Usually, you can have an oblique, a vertical asymptote together with an horizontal asymptote. You can have an oblique asymptote. You can have an oblique asymptote. You can have a vertical asymptote with an horizontal asymptote. You can also have an oblique asymptote with a vertical asymptote. And you can have an horizontal asymptote with a oblique asymptote. You can have all possibilities of asymptote, but this one, the case when you have an horizontal asymptote with an oblique asymptote, this can't happen. So either you have a vertical asymptote with an horizontal asymptote, like the one we saw, or you can have a vertical asymptote with an oblique asymptote. For example, here, you may have had actually this asymptote. Suppose you have x squared minus 1. So in fact, if this is x squared minus 1, then you end up with what? An oblique asymptote plus a vertical asymptote. Let us see this on... Here it is, sine x over x. Now sine x over x, it has what? It has an horizontal asymptote. You take the limit when x tends to infinity. You may have, this is an oblique asymptote. Why is it an oblique asymptote? Because the degree of the numerator is higher by 1 the degree of a denominator. Always when you have a degree, you can have here, for example, 4 and this is 3. Or you can have 3 and this is 2. Or you can have 2 and this is 1. So you have an oblique asymptote. Here, this is a nice example because it shows here you have a vertical asymptote at x is equal to 2. Why? Because 2x minus 4 equal to 0. At this particular value of x, which is 2, when you substitute 2 in the numerator, it's not equal to 0. And therefore, this is a vertical asymptote. So you have a vertical asymptote by when the denominator is equal to 0 at the point 2. And at the same time, you have a vertical, you have an oblique asymptote. This one here, you have a vertical and horizontal asymptote. You have a vertical asymptote as x equal to 2, and you also have a horizontal asymptote. When you take the limit when x tends to infinity, you get 0. And sometimes you only have an horizontal asymptote like the one we saw before. This is an horizontal asymptote. Of course, had we have put this x squared is equal to minus 1 equal x squared minus 1 here, then you would have an oblique asymptote along with a vertical asymptote. So in fact, we come out to the end of this lecture, and we investigated the meaning of limits, and we said that now we started really the topic or the course. This is the real beginning of the course, calculus, because you without limit you cannot define all concepts of calculus, like continuity and like differentiation. They have to rely on limit. And we said this is the most important thing. We said that the limit of a function, the function may not be defined at any point, and yet it has a limit at that point. So the important thing is not that the function be defined at the point. No, the important thing is that whether at that particular point at which we seek to determine the limit, when x approach this point A in a deleted neighborhood, because you are not interested at the value of the function at this particular point, whether f of x approaches another definite value, capital L, for example, a number, if this is so, then you say that the function has a limit. And we took actually different examples showing that, showing this limit, and then we talk about infinite valued limits. The limit does not exist, but it's a way of convenience of writing the function that it goes unbounded, whether from the right or left, it goes to infinity, and we call these vertical asymptote. We saw also that the function may have a horizontal asymptote, or it has an oblique asymptote. So with this, we finish one of the most important actually lecture. I hope you have gained and you have understood the subject of limit. And of course, this lecture, you may revise it on the platform of Uni-Nettuno Telematic University. And until we meet in our next lesson, I wish you good luck. And thank you very much.